All righty, so we left off with osmotic pressure. So remember, you have this system where on one side you have pure solvent, on the other side you have solution. So the side with solution is going to start to pull pure solvent through the semi-permeable membrane to dissolve its particles a little bit more. And so then your two sides are going to become unbalanced. Your osmotic pressure is the pressure you would need to press on the side that's going up. It's the amount of pressure that stops osmosis from occurring. So what pressure do you need to hold it right where it's at? And so your equation is seen down here, and we said that first character is what? Pi. It's a capital pi. So looks almost identical to the other one, but there's a slight difference. And MRT, what's that? So molarity. Yeah, so which constant? Ideal gas constant, and then temperature. Temperature in Kelvin. Okay, so you have a 0.15 gram sample of purified protein dissolved in water to give 2 milliliters of solution. The osmotic pressure is found to be 18.6 torr at 25 Celsius. Calculate the protein's molar mass. So again, yeah. What is molar mass going to be in? Yep, per what? Grams per mole. So we're looking for a way to get grams per mole. Okay, so I have grams. I need to figure out moles so I can divide the two. So if I write the osmotic pressure, well, that's awful. Out of excluding the gas constant, which of those will give you moles? Molarity. So I'm going to start there. Okay, so we're back to this gas constant. The temperature so 15 atmospheres for your osmotic pressure. Your molarity comes out to be 0.62. Is Yeah, it is 298. Whoops. Yep. Oh, let's see. Oh, because yep, I'm on the wrong problem. Never mind. Hang on. Let's redo this. I am looking at the wrong page. Okay, so let's use the right page. So there's our 298. Okay, so our pressure is in torr. Our gas constant is in atmospheres, so we'll translate That'll work a lot better. Now this will give us 1.0, 10 to the negative third moles per liter. And if you look, I have 2 milliliters of solution. So this will give me 2.0, 10 to the negative 6 moles of our protein. So then our molar mass the 0.15 grams from the problem. So 7.5 times 10 to the fourth grams per mole. So again, you want to look at what the problem gives you. You know molar mass is in grams per mole. Well, the problem gives you grams. So then you're going to have to look at the equation you have and say, well, one of these is going to give me moles. And I would not use the gas constant to solve for that. I would always make sure you're using something like the molarity or whatnot. And so then once you get there, you can say, well, I'm just going to divide the grams by the moles, and I got it. I think you guys do have your next quiz this week, though. We'll have to figure that out. I'll probably put it up on Canvas, and then you guys will take it, because we will not be having class on Friday. I will be at a conference for engineering education. So, yep. Because if we're going to start bringing engineering students in here, or pre-engineering students, want to make sure that we have a bead on what we're doing. Not yet. We're working on it. Right now, we're working on a deal with Colorado School of Mines. If we get it in place, what it'll do is it'll give students 4 years here for a bachelor's degree and a direct pipeline into a master's of science and engineering at Colorado. I don't know, Monday. Yeah. Wednesday this week. You are definitely an order. The problem is you keep getting things done correctly while procrastinating. You haven't been bitten in the backside yet because of the procrastination. So you're like, why stop a winning tradition? Yeah, then you got to rethink things. Once it doesn't work, then you got to rethink it. All right. Now, these are questions that you could expect to see on any number of exams. How would you prepare this solution? These are typically a little harder to think about. 1 liter of an aqueous solution of sodium chloride having an osmotic pressure of 15 atmospheres at 22 Celsius. Assume sodium chloride exists as sodium and chloride ions in solution. So the question becomes, we want to know the mass of sodium chloride that needs to be mixed into the solution. So we can figure out the concentration of the solution. Your temperature, this is where the 295 comes from. And this is going to end up giving us moles per liter. And just so you guys remember for the future, I never base curves off the very top grade. I base it off the first grouping. So there's usually 1 or 2 who are like astronomically like way up here. And so then it's like way up the next grouping, then I get a grouping that's still quite high, but it's like 4 or 5 people like right here. Like that's going to be the start. On the fire, on what exam? Oh, okay. Probably only because you felt bad because you felt left out. You're like, I'm just going to take this one on purpose. And I'll never tell anyone who actually set the curve unless you make me mad. Then I'll tell everybody and let you deal with it. No, I won't. So we have the concentration of this solution. So so this is the concentration in solution, okay? And solution is sodium and chloride ions. So then the question is, how do I calculate how much sodium chloride, like crystal, do I need to dump in here? If I have 0.62 molar sodium and chloride ions, what is the dissociation equation for sodium chloride? Okay, so what do I have to do to this concentration to get concentration of the original concentration of the sodium chloride crystal? Cut it in half. You see how the sodium chloride gives me 2 particles? This 0.62 is number of particles in solution. I have to cut it in half to get the concentration of the original sodium chloride. Mm-hmm. All right. Now I have 1 liter of this solution, okay? So I'm going to take my 0.31 moles of sodium chloride per liter. And then sodium chloride is 58.44 grams per mole. This is going to give me 18.1 grams sodium chloride. Now, how would I use this information to prepare the 1 liter solution? So I'm going to take these 18.1 grams of sodium chloride, I'm going to put them in a flask, put enough water in to dissolve all the crystals, and then I'm going to dilute to 1 liter. That will give me the proper solution. You don't want to put, so why wouldn't you want to put 1 liter of water in the flask and then dump in the crystals? Yeah, because it's going to increase the volume beyond 1 liter. So you want to dissolve those crystals first, then dilute to the 1 liter. All righty. Colligative properties of electrolyte solutions. So electrolyte solutions, what are the characteristics of an electrolyte? Conducts electricity, you have dissolved ions in solution. So typical salt water is an electrolyte solution. So we talked about this. So for example, 1 mole of your sodium chloride dissolves into 2 moles of ions. Now, we can account for the dissolving of these crystals by using what's called the Van Hoff factor. That's going to be the moles of particles in solution, moles of solute over moles of solute dissolved. Okay. Now, there are ideal Van Hoff factors and there are observed ones. Okay, so notice for sodium chloride, it breaks into a chloride and a sodium. So your Van Hoff factor would ideally be 2. Because if you did 1 mole, you'd have 2 moles of ions over 1 mole of sodium chloride. And so your I would equal 2. However, the observed Van Hoff factor is 1.9. Can anyone think of why that might occur? Why are we not getting the full dissolution into a Van Hoff factor of 2? When you know that the water, do what? Well, try going the other way. So you know that the water molecules are polar and they're going to interact with dipole ion intermolecular forces with the salt. But what does the salt do that's stronger than that? What kind of interaction does the salt have? Ion-ion. So you're going to have interaction amongst the solute ions, reforming some of the original sodium chloride. So your actual dissociation is going to go down a little bit. You're not going to actually get the ideal Van Hoff factor. Now, you notice here, all of your colligative property equations, they're the exact same equations. You just add the Van Hoff factor to the front of them, and you now get a correction for electrolyte solutions. So you have your boiling point elevation, freezing point depression, and osmotic pressure. All righty. So let's see. The freezing point depression of 0.091, what's the little m? It's not molar, it's molality. And I hate the word for it, it's molal. It's really awkward to say. But it's 0.91 molality, aqueous solution. What's CSCl? Cesium chloride. It's a fun little atom. It's what the atomic clock is based off of, because the oscillations of the radioactive cesium atom are very, very exact, and they will be for 10,000 years. So there's so many oscillations per second, and it's exact. Let's see. Yeah, that's what's it. So at 0.320 Celsius, the freezing point depression, where did I write? Hang on. Was I supposed to type that? Oh, okay. The freezing point depression of the aqueous solution of CaCl2, so calcium chloride, is 0.440 degrees Celsius. So these are your, so in which solution does the association appear, does ion association appear to be greater? So you have calcium chloride and cesium chloride. You put them in solution, they're gonna dissociate, but you're gonna have ionic interactions. In which one of those solutions are you gonna get a stronger ionic interaction? Okay, so, oh no, let's just start by looking at the calcium chloride. So your freezing point depression constant for water, 1.86 degrees Celsius for molality. So let's see, your delta T, I, AFM. Now what we want to solve for is I. Okay, so our KF is 1.86. Let's see, it's 0.091 mole. Our delta T, 0.320. Nope, that's for the other one. It's 0.440. For calcium chloride, our Van Hoff factor turns out to be about 2.6. Okay. Now, the question becomes, what is the ideal Van Hoff factor? What do you think the ideal Van Hoff factor is? The 2.6 is what we observed. What do you think the ideal is? Calcium chloride breaks into a calcium and two chlorides. Nope. You're making it harder than it has to be. You see, the calcium chloride breaks into 3 ions. So now, I actually looked something up that's kind of beyond what we do in this textbook, but it's a real easy equation. We're not going to derive it, not at this level. Absolutely not. That is going to be calculus on the level that's going to make all of you reconsider your lives. So we're just not going to do that. So this is called the degree of ionization. Okay, so your I is your observed Van Hoff factor. Your N is your ideal number. So 2.6 minus 1 over 3.0 minus 1 We get about 80% ionization from the calcium chloride. You would learn how to actually derive this in like chemistry 460 something. So I can teach you PChem if you want, but if you like the math, you would love PChem. Okay, now let's look at cesium chloride. So again, we're looking for that Van Hoff factor. So this one, so again, we have the 1.86 for water. Same molality. And then our delta T is 0.320. We're going to get 1.9 as our observed Van Hoff factor. So let's look at what is the ideal Van Hoff factor? 2. And so let's look at the degree of ionization. So we get about 90% ionization. So between these two, which one do you think ion association is going to be stronger? Nope, calcium. The calcium chloride dissociates to a lesser degree than the cesium chloride does. And it makes sense if you think of it in terms of Coulombic attraction. So the +2 and the -1 is going to attract a lot stronger than the +1 -1.
Would you just look at the charges determinant, or do you look at that?
If the charges are like very noticeable, then yeah, you can look at that. Sometimes you need to work it out because if you have like a magnesium oxide, yeah, you're going to have a +2 -2, but then you also have to take into account that that Coulombic attraction is going to be affected by ionic radius. So sometimes it's best to just really work it out. Mm-hmm. Oh, that you look up. These are that's your freezing point depression constant for water. Yeah, in your textbook, there's a table of these. And so you can see it has a list like it has water, benzene, a number of different solvents. And you would just look this up. This is unique to the solvent. All righty, that's that whole chapter. So, okay. We are going to start into kinetics. So, yep. We will work through the math. It really shouldn't be that bad, but if you're not a math person, just hold on. You're gonna have to white knuckle this one. You never heard that? Yeah, it's like you're going so fast, like you're holding on to the steering wheel for your life. And it squeezes all the blood out of your knuckles. Not to your knowledge. Absolutely not. Yeah. You either have blood in a system or you don't. Okay, so reaction rates. Here we see the dissociation of ammonia into its constituent nitrogen and hydrogen. Now, you're seeing some sort of notation you may have seen a little bit, but let's make sure we understand it. You see the brackets? Brackets is concentration. It usually means molarity, moles per liter. So the rate of either disappearance or of rate of disappearance of reactants and appearance of products, we're gonna have a very same equation. And it's gonna be the concentration at some time two. So it's gonna be the delta of the concentration over delta T. Now, notice these nice little curves here. So these nice little curves. So you can see as ammonia disappears, nitrogen and H2 both appear. But you notice how the H2 curve is much higher than the N2 curve. Well, we want to try to explain that mathematically. Keep in mind, we're trying to suss out reaction mechanisms. The reaction mechanism is the various steps needed for an overall reaction to occur. And we'll usually give you what's called intermediates along the way. An intermediate is a compound that's formed during the process of a reaction mechanism. It's formed and then completely used for the next step or some subsequent step in the mechanism. So let's look at some numbers here. I put that up because that was really kind of like my interview here. Tell us about yourself. You want the truth? No. Now, you can see we go from 0 to 400 seconds. We have ammonia disappearing into an H2 appearing. Concentration is changing for each one. So let's look at these over different time scales. Okay. So if I go from 50 to 100 seconds, let's just do the rate of disappearance of NH3. So from 50 and 100 seconds, we have, oh no, that's that number and that number. So this is going to be 0.065 minus 0.079 over 100 minus 50. We end up getting a negative 2.8 times 10 to the negative fourth moles per liter times seconds. Now, of course, that makes sense. This is the reactant. It's being used, so we're getting a negative number. But it does tell you about how you express the rate as we go forward. So for the rate, for example, of disappearance of any reactant is going to be the negative of the rate expression. In more general terms, that'd be negative than whatever compound A happens to be. Okay, but let's look at the appearance of both N2 and H2. Okay, so delta T. So we'll pull our numbers from the table. This is going to give us 1.4, 10 to the negative fourth moles per liter times second. Okay, and then let's look at the appearance of H2. So now we have the rates of all three of these compounds, both disappearing and appearing as products. Now let's start looking at some ratios. Okay. I'm going to say, kind of let it run there. The rate of the disappearance of NH3 over the rate of the appearance of N2 comes out to be 2. So if we multiply through, we're going to get the rate of disappearance of NH3 is going to be 2 times the rate of appearance of N2. Okay. Let's compare H2 and N2. Because I chose that because if you look at the equation here, N2 is the one without a coefficient. So I'm trying to compare everything to that. You can compare the others if you want to, but you're going to start getting fractions of like 2/3, 3/2. Okay, so the rate of H2 to the rate of N2 this gives us the value of 3. So our rate of appearance of H2 is going to equal 3 times the rate of appearance of N2. All right. So we got that. Let's look at a longer time scale. Well, you're going to use the exact same procedure, but at some point, look at, where we go? Sometime look at 150 to 300 seconds. Because again, you're just going to take numbers from the table and you're going to do this same process over again and see what the ratios end up being. You're going to see that you get these exact ratios over again. Now, on a longer time scale, like this, like your rate of H2 to N2 will come out to be about 3.1 after rounding, but you're going to round that down to 3. Your other one, your ammonia to nitrogen rates is going to come out to be about 2.1, but still, you're still getting these overall same ratios. Okay. So what does that tell us? My rate of ammonia consumption is 2 times the rate of nitrogen production. So remember, this rate of ammonia consumption is a negative. And then 2 in the rate of ammonia production, or nitrogen production. What we're actually going to do is move that 2 to the other side. So we have that relationship. Then my rate of H2 production is 3 times my rate of N2 production. So I remember what these equations are. Going to move that 3 to the other side. We're going to get 1/3 Now let's set all these equal to each other and see what it looks like. Because remember that our equation two ammonias is going to split into N2 and 3 H2s. And if our overall rate, well, at least our rate expressions, we're going to have -1/2. Then we'll have our rate of N2 equals 1/3 our rate of H2 production. You start to notice that these rate expressions are going to be using the coefficients for the fractions. You see that? So you're going to have to multiply each one of these rates by a fraction where the coefficient is in the denominator of that fraction. And so generalized, so there for a generalized chemical reaction of A plus B yields C plus D, our rates are going to match this. No, I have to fix that. No, I don't. Okay. You notice how the reactants get a negative sign, the products get a positive sign because the reactants are being used and the products are being formed. But again, you have to multiply each one of them by a fraction where the coefficient is in the denominator. Okay, we'll call it there for today. Oh, up here. What? Yeah, so yeah, the reactants, no, the ones regarding the positive.
Oh, yeah, I thought it said.
Ones on the left are negative, the reactants. Products are going to be positive. The negative sign goes on the compound that's being used. The positive sign goes on the compounds that are being made.
No.
Forget so many of these phrases you don't even are not popular anymore.
I feel like that's still